Right. Do I start whenever?
Yeah, you can start, and I will give you a signal when you have 1 minute.
Okay, great. Thank you. Uh, Morning, everyone. So I have the pleasure of going first. My topic is centered around low carbon retrofit solutions in UK, and it's at the intersection of whole life carbon, performance gap, and behavioral science. I'm from Ramboll, and I wrote this with a professor at the Architectural Association, and we both did the Sustainable Environmental Design course. If this works. Sorry. Oh, thanks. Okay. So the topics I'm trying to investigate are behavior in occupancy and also how to bridge that performance gap we have in London retrofitting. And to start off with, my hypothesis is probably best graphically represented in this graph. On the x-axis is depth of fabric retrofit, which is the amount of interventions you would include in your building. And that's mapped against the operational carbon reductions. And if you can imagine a linear embodied carbon increase when you add insulation, that would give a diminishing returns in insulation. And that's the graph that I'm trying to plot. But at some point when you retrofit to an extent, you'll have a jump in embodied carbon because you would need to implement mechanical systems. And that's to regulate internal conditions and carbon dioxide, VOCs, and humidity. You can see that mostly in EnerPHits and retrofits where they put in mechanical heat recovery systems and etc. So this hatch on the left is the point in which the embodied carbon justifies the operational carbon reduction. And when there's things that don't really affect the social value or aesthetics of the building, like insulation, there's a heavy argument about justifying the amounts that you actually put in, be it XPS or wood fiber, to the carbon reduction. And basically my hypothesis is that you can redirect the amount of carbon you invest into the building using behavioral interventions instead of mechanical systems. And that's that blue line over there. So this hypothesis we tested with the backdrop of the Trellick Tower in London, and it's a social housing block in the Kensington and Chelsea borough, and it's a grade 2-star listed building, which means that the facade is protected and you would need to get extensive planning approval for any window improvements. And what we had the opportunity to do is get occupancy interviews and also data logging. And the data logging helps us with the behavioral performance gap because it helps us calibrate our thermal models. And also with our interviews, we could input that into our occupancy schedules. So we would know the kitchen appliances, the internal gains, the loads, and then when each room is occupied. And these were all fed into our Grasshopper script, which we simulated everything on EnergyPlus on Rhino. Just to test the three scenarios, the first one we did was the EnerPHit solution, which is a very popular retrofit strategy in London at the moment. And it faces the performance gap in a way where you trap in as much of the air as you can inside the thermal envelope, and then you recover the heat whenever you ventilate. And this uses a lot of the building physics that we know of, increasing the insulation to a very good depth and also air tightness improvements. And just to summarize some of these interventions that we plotted, we basically modeled everything in really minute detail on Rhino because we could then easily get the volumes of each material and apply a carbon factor to find the whole life carbon emissions. We put in external cladding with a bit of insulation, hygroscopic internal insulation, so that it maintains its vapor open construction. This is a thermally massive 1960s building, and we wanted it to breathe so that it wouldn't have any humidity risk. And obviously, in EnerPHit standard, you would have a mechanical heat recovery system with primary and secondary ducting, and we modeled that all in depth. And this reaches around 25 kilowatt hours per meter squared annually of heating demand. Another option here is the internal insulating option, which is what you see in social housing that are listed. This one, we took inspiration from the Sheffield one, which was made by, I think, Wolfiston or maybe Stride Treglown. They had a very interesting thermal bridging detail at the balcony to make sure the insulation was continuous. And we also did this example just to show what kind of carbon differences we can see in external and internal insulating. And what I want to address is that we right now we build at a fabric first methodology. We do fabric and then implement systems. Then we look at renewables and we offset that. And that's how we drive down carbon. I want to find a way of implementing more free winds and using our occupant behavior and our biophilic nature that's inherent in our bodies as part of the design. And those two highlighted items, the first one is what I would say are free winds, behavioral and habitual changes. So in this case, what we did was just swap rooms where it was applicable, and it was reflecting the circadian rhythm of how rooms were used, and as well as the diurnal shift of the temperature, and find which part of the building should be used at what time. And those are free things you can do without changing the building fabric. Fabric improvements we'll get to later because it is still essential in improving anything. But then after that, there is space for adaptive design elements. And what I mean by this is things that you can change, the building fabric that you can change from occupant behavior. So what we modeled here was secondary glazing that was removable. There were wool and solar curtains. Wool curtains would change the U value of the composite element of the wall, and solar curtains that block out or reflect light. And then the biggest intervention here was the winter gardens, where we basically used the balcony to create a winter garden for the room. I was touching on fabric improvement just now. I think we still have to respect that fabric improvements are by far the most effective way of improving architecture. And here we preserved a lot of the passive house elements of fabric improvements, such as maintaining continuous insulation, sealing the gaps on the skirting and any spalling of the concrete. And then for this example, we actually left the southern balcony exposed because it was concrete and thermally massive. And then things like airtightness tape were applicable, and sealing the windows, and etc. So on the thermal modeling side, we wanted to prove it quantitatively that you could kind of reach the same heating demand reductions by adaptive means as you do with a EnerPHit retrofit. And what we did was, for every adaptive element, we would model it on Grasshopper and use a logic system. And this logic system kind of emulates human behavior. So if you're in a room that you are going to use, you wouldn't draw curtains if it was negative to your work. And so these things would spiral down, and at any point where it affects the building fabric, we would find a way of making it beneficial to the thermal comfort of the occupant. And then on the bottom, there's the graph of showing the heating seasons being much lower. This is a more granular detail of a weekly occupancy, and it shows the daylight quality as well, because in an adaptive area, you can actually get a lot of benefit from having an open space. This is the cooling season, and how the overheating potential is much decreased because you have a thermal buffer from the winter garden. As I was talking about earlier, the carbon emissions, we basically routed on Grasshopper on a carbon factor. And to just introduce a new metric, this is the carbon efficiency per heat demand reduction you achieve. And you can still see that fabric is probably still the best option. And then systems is at the bottom. But there's something in between where we can actually tweak the way we retrofit things, where we want to use secondary glazing and winter gardens because they have a medium amount of whole life carbon intensity for the percentage of heat reduction you get. And I want to just leave the thought of overheating and resilience here. We're going to face a cooling season that's going to get larger over time. And the more adaptable the architecture is, the more resilient it is. And behavior is quite intuitive, and it's things that you see every day to day. And actually, a social housing block that is so repetitive, you can kind of introduce behavior changes through seasons, and that acts as a part of the design language as well. And it will help us inherently be more biophilic. Yeah, thank you. Did I go over time?
Right on time.
Great.
Good job. Thank you, Brian, for the excellent presentation. So do we have any questions for Brian? All right, thank you, Brian, very much.